Deep inside a tropical, high-density data center, thousands of servers pull massive amounts of electricity to process data. As a byproduct, they generate immense, relentless heat. Under normal conditions, a precisely calibrated air-cooled chiller plant absorbs and rejects that heat into the atmosphere, keeping the facility stable. Then, the primary utility grid fails. The facility goes dark. The chiller compressors and condenser fans immediately lose power and halt. The IT equipment, however, is backed up by uninterruptible power supplies. The servers never power down, which means they instantly continue generating a lethal level of thermal energy into the data halls, even as the primary cooling systems sit idle. Air-cooled chillers are heavy and highly complex machines. They are bound by physical limitations like the rotational inertia of massive compressors and the required boot-up time for their onboard logic controllers. To safely navigate these mechanical thresholds and return to 100% capacity, an air-cooled chiller requires between 120 to 180 seconds. At T0, the white cooling duty line plummets to 0. Above, the flat orange line, the IT load, never drops. Servers keep pumping heat. The empty void between them is a 3-minute transient window where the plant absorbs no heat, risking rapid thermal runaway. Surviving this exact transient window requires strict engineering across 3 disciplines. We call this the resilient plant equation. It demands highly isolated power topologies, a mathematically precise thermal bridge, and synchronized telemetry to verify actual heat removal. Procuring extra chiller units to achieve physical N+1 redundancy offers no protection here. If the plant's underlying electrical and mechanical architecture cannot successfully bridge this specific 180-second thermodynamic gap, the facility will overheat and shut down. The recovery sequence begins immediately. Between 0 and 15 seconds, the facility detects the outage and the backup generator begins supplying a usable alternate power bus. Looking at the power architecture, we see the isolation required to survive. Source A, the utility grid, drops offline, but Source B remains ready. The generator engages, feeding path B. There is no shared bus, eliminating the risk of a crossover fault. To prevent a single point of failure from disabling an entire chiller, this philosophy of true dual-power terminal blocks must extend all the way down, physically terminating inside the individual chiller frames. While the heavy mechanical components wait for generator power, the local logic controllers managing those machines face a brief, chaotic voltage gap. If a controller loses power, it triggers a mandatory reboot sequence that adds minutes to the recovery timeline. To prevent this, dedicated protection sits directly within the power path. Uninterruptible power supplies, or UPS modules, feed the localized programmable logic controllers and variable speed drives. Retaining UPS power for these controllers preserves their active memory and anti-cycle permissives. The chiller remembers its operating state, preventing it from triggering catastrophic hard-coded lockout delays during the transition. Once the generators assume the load, a secondary electrical threat emerges. The massive power draw of chiller compressors attempting to restart creates severe harmonic distortion, which can cause premature breaker trips on the backup generators. To maintain generator stability, active front-end variable frequency drives are integrated directly into the chillers. These multi-pulse guides progressively filter the electrical draw, capping total harmonic distortion below 5%. Without this fiercely isolated and heavily conditioned electrical foundation, the massive chillers lack the clean power and retained logic memory required to even attempt a safe restart. At 15 seconds, the electrical power is stable, but the compressors remain locked out by the plant's control system. This control sequence diagram lays out the mandatory safety checks. Local permissives require proof of power, healthy safety parameters, and correct valve positions. Once met, the logic triggers the hydronic circuit, sending the command to start the chilled water pumps and secure a definitive proof of flow. Evaporator flow must be proven before a single compressor is allowed to fire. If a compressor activates while the water inside the evaporator is stationary, the fluid will rapidly freeze, fracturing the internal plates and destroying the chiller. Down on the mechanical floor, motorized isolation valves rotate open. The variable speed pumps spool up, pushing thousands of liters of fluid through the piping to establish the primary chilled water path. This entire sequence strictly adheres to the manufacturer's rapid restart mode. Local mechanical safeties, like low-pressure thresholds and flow switches, are never bypassed or overridden for the sake of speed. Rushing a compressor start without first verifying hydronic flow does not restore cooling to the data halls. It destroys the chiller, releases refrigerant, and permanently compromises the chilled water loop. At 60 seconds, hydronic flow is proven. The control system sends the final command, and the first compressors begin to spin. Even though the compressor motor is drawing current and rotating, the thermodynamic cycle is just beginning. The actual cooling duty being absorbed by the refrigerant is still negligible. Returning to the thermal bridge graph, we see how the facility survives while compressors load. The blue zone represents thermal energy storage discharging into the system. The engineering overlay calculates roughly 38 cubic meters of storage is required to bridge this specific energy gap. This TES tank acts as the thermodynamic bridge. It injects a precisely calculated volume of pre-chilled water directly into the supply headers, actively absorbing the IT heat while the mechanical chillers are still catching up. Sizing this tank is dictated by hard physical variables: the total protected load, the target time required for the chillers to recover, the density and specific heat of the fluid, and the maximum allowable temperature rise in the data hall. Operating in a tropical climate introduces a severe complication to this timeline. The plant must navigate the physics of rejecting massive amounts of server heat into an outdoor ambient environment that already sits at 40 degrees Celsius. If the system rapidly stages its condenser fans in extreme heat, it creates an aerodynamic risk. Hot exhaust air can be pushed down and recirculated back into the air intakes, rapidly spiking the condensing temperature and triggering high-pressure trips that shut the chillers back down. Proper physical plant design mitigates this recirculation risk. Units utilizing an open V-bank coil design and vertical heat discharge force the staged high-velocity hot exhaust air up and away from the equipment, preventing it from looping back into the intakes. The TES tank provides the mathematical certainty to keep the servers alive. It buys the chillers the necessary time to slowly and safely navigate the harsh physical limits of a 40-degree environment without triggering a high-pressure shutdown. At 180 seconds, the chillers are fully spooled up. On a monitor in the control room, the building management system flashes a green indicator confirming the compressors are running. Relying on a Boolean, true or false, run status on a computer screen is a critical operational flaw. A green light confirms electrical current. It is not empirical proof that the plant has actually recovered its capacity to cool. To prove actual heat absorption, we rely on a specific thermodynamic equation. The capacity, Q, requires live data inputs for the mass flow of the water, its specific heat, and the precise temperature differential across the evaporator. All three of these variables must be captured and calculated on a single, synchronized clock to be valid. This requires stringent 1-minute measurement and verification tracking. By aligning flow, temperature, and power data simultaneously, engineers can plot the actual, realized recovery curve of the plant's capacity. Without synchronized thermal telemetry, facility operators are flying blind. They are forced to assume the plant is absorbing heat when the equipment might just be spinning its compressors without transferring any real energy. Theoretical design margins mean nothing until they are tested. The ultimate proof of the recovery sequence is the Integrated System Test, or IST, which simulates a complete black start blackout while the facility is under a representative IT heat load. This Integrated System Test dashboard shows exactly what is tracked during the blackout simulation. The execution tracks a strict chain of verified events. It logs the exact second the automatic transfer switch engages, the proof of flow, the first compressor firing, the plant crossing the 80% capacity mark, and the final achievement of full duty. The pass criteria are absolute. The data hall's thermal envelope must be maintained for the entire duration without triggering uncontrolled pressure spikes or losing flow. The evidence capture proves this by logging the simultaneous flow and temperature calculations minute by minute. The integrated system test forces the facility to prove its theoretical design margins can actually survive the physical, chaotic reality of a total power loss. Looking back at the resilient plant equation diagram maps out exactly what makes an air-cooled data center truly resilient. Surviving the thermal gap requires three non-negotiable pillars working together: the engineered margin of the thermal buffer tank, a fiercely independent power architecture, and synchronized telemetry providing actual evidence of heat transfer. A Tier 4 air-cooled chiller plant is not achieved by purchasing equipment based on brochure claims. It is engineered by systematically eliminating common-mode electrical failures, bridging the physical thermodynamic gap with calculated thermal storage, and proving execution through unrelenting, time-aligned empirical evidence.